In this video, I want to solve the third problem that you see here from this calculus exam. This third problem asks us to prove that the following function, f of x equal to 0 for x less than or equal to 0, or equal to the exponential of minus 1 over x for x greater than 0, admits the first derivative and the second derivative at the origin. So I want to solve this exercise, this problem here. And well, the function has the following shape. It is quite easy to, let's say, to sketch it. Here it will be 0 for x less than or equal to 0. And at the point x equal to 0, it will be something like this. It will behave exponentially in this manner. So for x very large, the function will approach the value 1, because in this case, minus 1 over x will be close to 0, but the exponential of 0 will be 1. So for x approaching infinity, the function will approach the value 1. So this is x, and this is the function f of x. It will behave like this. We need to show that the first derivative at the point x equal to 0 and the second derivative exist, and they are equal to 0, because that's the only possible value that they can have. And this will be very easy to show. Why? Well, because let's take the derivative of the exponential function. So the derivative of e to the minus 1 over x. This is what we want to calculate. This derivative is simply equal to e to the minus 1 over x times 1 over x squared. And if we calculate the limit as x approaches 0 from the right, so 0 plus, and here we have e to the minus 1 over x times 1 over x squared, which is the derivative of the function e to the minus 1 over x. It is very easy to show that this will be equal to 0, because the exponential e to the minus 1 over x will decrease much more rapidly than this function increases, because when x is small, this function will be very large. But this function here will be way smaller because we have an exponential. And it is very easy to show that this is 0, for example, by using the L'Hopital, because you can rewrite this as 1 over e to the 1 over x times, you can rewrite this as, well, you can put x squared in the denominator, or you can put 1 over x squared in the numerator. So you can rewrite it like this. And you can also change the variable. So we have to calculate the limit as x goes to 0 plus, or you can calculate the limit as y goes to infinity. And here you have y squared over e to the y. So you're changing the variable from x to 1 over y, basically. But here you can easily use the L'Hopital. You can use the L'Hopital twice. So the first time you have limit as y goes to infinity 2y over e to the y. So you're taking the derivative of the numerator, and then you're taking the derivative of the denominator. If you take the derivative one more time, in the numerator you just have 2, and in the denominator you still have e to the y. And as you let y go to infinity, this will be 0. So it's very trivial. You just use the L'Hopital. And so from the right, the limit of the derivative is 0. And also from the left, because the derivative of this function is still 0, because this is y, or f of x, if you want, equal to 0. So you take the derivative of that and you get 0. Something similar for the second derivative. So the second derivative is simply the derivative of the first derivative, but the first derivative is e to the minus 1 over x times 1 over x squared, and you take the derivative of this. Well, the derivative is simply e to the minus 1 over x, and then you have 1 over x squared minus 2 over x cubed. But also in this case, you can show that the limit as x goes to 0 plus of this function is 0. because the exponential will decrease more rapidly than the polynomial terms of the kind x to the power n. In this case, where x is equal to 4 and 3, because 1 over x squared to the second power is 1 over x4 to the fourth power. So also in this case, you can show that the limit goes to 0, because this function will decrease more rapidly than these polynomial terms explode, because they will increase, but the extent to which they increase is not enough to make the overall function, this one here, the second derivative from the right, this function will not explode, even if these terms will become large, because this one, as I said, will become way smaller. So this is how you solve the problem, this problem here. You can easily show that this function, defined in this manner, admits the first and the second derivative at the origin, and those derivatives are simply equal to 0.